At this stage, they are being used to estimate forces from the knowledge of flow rates. So, this question of so suddenly it's blue now. Okay. Oh, I can choose the color. Okay. I didn't know that. So as they say, the more you live, the more you learn. So we talked about the quiz. Now, if students keep coming in at will, say I am not disturbed. It's the class that is disturbed. So we have a quiz tomorrow talking about equations of motion. Related to mass, momentum and energy. Energy we will start on Friday. So, to that extent, see, this book has energy equations spread out over a few chapters. So, when you get into energy equation chapters 3, 4 and 5, they all blend. So, we looked at local approach, global approach. And right now, we are pursuing a global approach involving a control volume formulation. So, here we distinguish between near field and far field. You do not have to, because once you can pick any control volume you want, but if you choose the control volume carefully, then the integrals can be estimated reasonably well. That is the idea. So, if you pick your outer boundary to be in the far field, can you think of one advantage we gain? What was the advantage? Yeah, there are many advantages at intermediate stages, but ultimately you were able to say that force acting on the control volume can be transferred equal and opposite to force acting on the object inside. Okay. So, the forces acting on the far field boundary did not have a net contribution. That was the main advantage of having a far field. But in general, in almost all fluid mechanics problems, when you see a problem, you ask, is it internal flow or external flow? Okay. So, there is no far field in internal flow. If you recall the flow through a tube problem, pressure was decreasing all the time along the length of the tube. There was no recovery of pressure, which happens in an external flow situation. Okay. So, if you introduce an object in a flow field, locally the field is disturbed and then it recovers. So, that is external flow, where far field comes into picture. So, there was this other question that some students asked related to evaluation of integrals. Now, I have to confess, not just this course, any course is built on or built up on all previous courses you have studied. So, it is expected that you know some elements of physics, some elements of thermodynamics, mathematics. So, if you are given a simple differential equation, you will not have any trouble solving it, or some vector identities. So, should be, you may not remember, but you should be able to access a book that will give you the necessary details. So, in this course, what we study later will rely on what we have studied now. So, there is some, you may call it, continuity in discussion. So, if you come late or you miss a class, it gets interrupted and you won't be able to follow the conversation. So, coming on time is not just an issue of discipline, but it's also this continuity in conversation and also helps you recall what you have done in the past. So, let us say this is a control volume. Let us say this is inflow, this is outflow. And you have to evaluate an integral of this type, integral over C s u dot n d s. By the way, I think this dot is visible. I don't have to darken it, right? Actually, when you write dot, it should be centrally placed. If you keep it at the bottom, it is like a decimal place, 2.3. If it is at the center, it is a dot product. So, trying to evaluate this integral. So, this is written as a to b plus b to c plus c to d plus d to a. I am doing this in detail because you will have to do it often. There should not be any confusion on how it is evaluated. And these integrals are with respect to, okay, this is a 2D geometry. That means, the third dimension is taken to be just, let us say, unit dimension. So, you do not have to worry about that dimension. Then in that case, this surface area can be written as d lowercase s, where lowercase s is a local coordinate that goes along the control surface. So, it is integral a to b ds, b to c ds, etc. But we also have a fixed Cartesian or any other cylindrical coordinate system. We often carry out such integrations in an orthogonal coordinate system. So, let us say Cartesian, in which case x and y. So, for A B, ds is dx. Okay. So, so this will be u times u dot n on that surface, let us call that V 3. Okay. So, the flow is taken to be in that direction, and the unit normal is also in that direction, but if it is, let us say in that example of flow over a flat plate, so this of course turns out to be 0. So, the surface is not permeable, it is impervious to flow. So, it blocks flow in that direction. So, it just turns out to be u times 0, which is 0. When you go from B to C, d lowercase s is dy. So, that becomes u2 square dy. This is plane 1, plane 2. Now, for CD, so this is integral from C to D of ds. So, let us write that as u v 4 ds, which is now x is in the rightward direction. So, it becomes minus dx. Okay. So, now you can write this as integral d to c u v 4 dx, and then approximate it as I think we had chosen in the previous calculations, C D was taken to be the far field, and we set the x velocity equal to u 1 v 4 times w. And then from D to A, this is using the same logic, convert integration from D to A as A to D, replace ds by minus dy. Okay. So, those two negative signs they cancel off, and you will get minus u 1 square times h. That negative sign arising from u dot n, u is in the rightward direction, n is in the leftward direction. So, that will give you a negative sign. Okay. So, either you can use your judgment, but in case you have any doubt, you can explicitly evaluate, but make sure that you split. It is not that you write A B plus D C, you can't write arbitrarily. You have to go in that sequence, as you know from your basic courses in mathematics. Integrating over a surface, you have to maintain that sequence in which the integral is split into smaller ones. So, we were looking at an example So, I think subconsciously we have been assuming flow to be steady incompressible. If any of these conditions is violated, then I will explicitly say so. This is flow in a bend, it is an internal flow problem. So, this is sometimes called a reducing bend. Why reducing? Because the area of cross section is decreasing from A 1 to A 2. Now, when you, so this is the solid wall. if you look at numerical problems given in the book, the forces turn out to be substantial. So, you can always think of your hostel, and then wherever you see a bend, suddenly be alarmed. There is a bend over there, we have to be careful. Okay. So, there will be, of course, you have to apply force on the fluid to turn it around. Equal and opposite will act on the tube, and equal and opposite will act on the support that holds the tube in place. So, if there is any fluctuation in flow, that will induce a time dependent force on the bend, and you may have seen those bends moving quite violently, leading to, well, you might have studied some basic courses where you know that the strength of a material suddenly gets lowered if it is subjected to time dependent forces. So, if everything is steady, it behaves very strong, so it is great. But if the forcing function is time dependent, its strength is much lower. So, time dependent forces are a huge problem. So, from that angle, all the steady state calculations we are carrying out are, we call them conservative. Everything is peaceful, then everything is going on all right, then these are the forces, and probably the structure is stable. But if time dependence sets in, then there is cause for alarm. Okay. Of course, you do not have to be really alarmed. See, that is where your knowledge of the subject helps you overcome unexpected behavior, either in terms of the material or in terms of the fluid. So, it is an internal flow problem. This is P 1. So, you will not refer to any far field condition. Pick a control volume, A, B, C, D. Of course, A, B and C, D are part of the same surface, and u dot n is 0. So, applying mass balance, you will get minus u 1 A 1 plus u 2 A 2 equal to 0. And from the momentum equation, so now, in previous examples, we wrote only the x component of the momentum equation, but here you can see that the flow direction has changed. So, you have to write two components of the momentum equation, f x, f y. So, f x is equal to, well, on the plane B C, the x component of velocity is 0. So, there is only one component. On the side boundaries, u dot n is 0. So, it is only an inflow component. So, minus rho u 1 square A 1, and similarly f y is equal to rho u 2 square A 2. Okay, this is the sum of all external forces acting on the control volume. Now, you want to extract that part of the force which is acting on the bend. The bend is the solid material which turns the flow direction around from horizontal to vertical. So, this f x, so let us call this f x bend. So, you can start showing the stress distribution on the control volume that will enable you to extract force acting on the bend. This is the bend. So, in the x direction it is pressure. So, F x bend plus P 1 A 1 will be equal to minus rho u 1 square A 1. So, when you write it in this form, you get the x component of the force acting on the bend itself. Okay. So, now you have gone from the control volume to the bend. Similarly, F y bend. Now, on B C we show pressure acting normal to the surface, right, with that sign notation symbol. So, plus well it is minus P 2 A 2 equal to rho u 2 square A 2. So, F x bend and F y bend, these are the forces acting on the side surfaces of the control volume, and equal and opposite will act on the solid material. So, these are to be interpreted as forces acting on the side surfaces of C V. So, if you show just the tube, this solid material, maybe we can show it with So, now you can imagine this is the tube itself, and on this it will be the forces acting on this tube would be minus F x bend and minus F y bend. Okay, where F x bend, F y bend are to be found from these two equations. Okay, so, applying the momentum equation, you get these two simple equations, and then these two simple results, and then you can interpret the results a step forward by localizing the general result to portions of the control volume. It is an important application of the momentum equation to the problem of jet impingement over a curved vane. I think the word used in the book, it also uses the word bucket for a vane, because historically these hydraulic turbines also used the normal bucket to turn the or deflect the jet. So, we will use a technical term called a vane leading to a device called a turbine. We are thinking of water as the fluid medium. So, it is a water jet, and the turbine would be a hydraulic turbine. So, at the scale of a curved vein, so jet velocity is u and cross sectional area is a. Therefore, the mass flow rate of the jet is rho a j u j. It is impinging on the jet on the vein. In the first part of the problem, the vein is fixed and this flow will then come out. So, you can see that the flow is now turned around. So, we can apply the momentum equation to the control volume. So, on the solid surface u dot n is 0, and then on the free surface we take it to be a stream surface. It is like a stream tube, that means all the flow is directed, flow is going around like that. So, there is no velocity component. So, the surface, so it is like a circular jet coming and hitting a curved vein and remains in this idealization, it remains circular. Will it really remain circular? Now, at this point of analysis we do not know, because any change in the cross sectional shape of that jet, it is a local effect and our analysis is global. So, global analysis will not tell you whether the jet diameter is decreasing or increasing. All you can do is assume no change in the jet diameter, it comes out like that. And the free surface, what is the free surface? It is the surface interface between water and air, it is a free surface. It is called like a free surface where atmospheric pressure acts on that surface. So, on that surface again, because it is a stream surface, u dot n is 0. So, f x is equal to minus rho u j square, I am sorry, now on this is minus u j square a j is on the plane A D. Now, on the plane B C, u dot n is again u j, but the flow direction is minus u j. So, once again you have minus u j square a j. So, this is minus 2 rho u j square a j. Now, we have shown a vein where the flow direction is completely turned through an angle of 180 degrees. That is not necessarily the case. There are many problems in the book where the vein deflects the flow through some angle alpha. We looked at an example of a vertical plate where flow angle is the flow is turned through 90 degrees. U dot n is positive, because n is that way, flow is also that way. but the other term in that integral is u, which is minus u j. So, this is f x acting on C v. Okay. So, now how much of this force is acting on the vane itself? Well, on the free surface it is atmospheric pressure, everywhere it is atmospheric pressure. Okay. So, pressure there is no, this is external flow. So, unlike internal flow problem of the bend, here there is no contribution because of pressure. How about shear stresses? So, we are treating velocity, this jet there is no change in area, jet turns around. So, the velocity distribution on any plane is uniform, it is constant across a plane. So, there are no shear stresses, which means this entire force is acting on the vane. So, force on the vane, so equal and opposite. So, if you think of the vane, so I am showing this shaded thing as the vane, and there is a force acting on it which is minus f x, which is 2 rho u j square a j. This is the force acting on the vane. Now, how can it be made useful? So, here let us say you allow the vane to move at constant speed. Okay. Now, if you apply force, it is going to accelerate. Okay. So, you need a very special arrangement to make the force make the vane move at constant speed. Okay. So, one possibility is to mount the vane on a shaft and force the shaft to rotate at constant RPM. So, usually it is easy to force constant RPM on a shaft, which will give constant velocity. Okay. So, if the vane starts to move at constant speed, how will the analysis get changed? So, you know from your knowledge of high school physics that that in classical mechanics the laws of nature, mass, momentum, energy are invariant as you go from a stationary frame of reference to one that is moving at constant speed. If it is accelerating frame of reference, then the equations have to be corrected for that acceleration. But if it is constant speed, then just replace u j by u j minus the vane velocity. So, now we let us say the vane is moving at constant speed u, then force acting on the vane is equal to 2 rho a j u j minus capital U square. Replace absolute velocity by the relative velocity, and the power transfer to the vane is the product of force and velocity. So, the next question is, of course, if your goal is to use this vane in as a device like a hydraulic turbine. So, you have a jet. Now, how do you create this jet of water? we will look at some examples in the energy equation part of the syllabus. You will study that it is possible to convert potential energy into kinetic energy. This is an everyday observation that an object kept here, if I leave it, then it accelerates, your potential energy gets converted to kinetic energy. So, similarly, a body of water kept at some elevation, it could be a reservoir at some altitude, and then you have a tube at the base, and then water will just start gushing out, okay, with the gravitational potential getting converted to kinetic energy. So, there are natural reservoirs, so it rains and you have collected water over there, and then you can use its gravitational potential convert into kinetic energy and to produce a jet of water. So, this jet of water is a natural resource, and then you want to convert it into, let us say, useful work. So, if you have a shaft that is rotating, then we have, I do not know if you have done courses in electrical engineering, it is again, I do not want to say it is straightforward, but it is possible, the know-how is now available. So, you can convert that rotation into electrical output, which of course, now feeds all these lights and this microphone and screen and air conditioning and everything. So, electrical is like a very useful handy form of starting point for our everyday living. So, you can convert a natural reservoir of water to a jet of water to a rotating shaft, where it is this vane which is now allowed to move at constant speed. It moves at constant speed because of the configuration of the vane being on a shaft. So, this is a shaft. So, on this you have mounted a vane on which there is a jet of water. Okay. So, the analysis is for this instant, because at the next instant the jet is no longer a curved vane turning the flow through 90 degrees. So, really speaking, it has become an unsteady problem, because as the jet is moving, its orientation is changing. So, the calculation is for that instant. Now, how do you do analysis when jet, the vane is like this and jet is at an angle? So, I mean, it is a little more, yeah, I saw you. It's a little more algebraically involved, but possibly if you are in the correct discipline, then when you analyze turbines at great length, you will be able to carry out those calculations, where the vane is not exactly oriented the way you want for this analysis. Okay. So, from this application viewpoint, you want to pick uj and capital U, the jet speed and the vane speed suitably. You can see that let us say the vane is fixed, then capital U is 0. So, no power is transferred. Similarly, if the vane is allowed to move at a speed equal to the jet speed, then no force is developed, uj minus u is 0. So, naturally somewhere in between there is a point where the power transferred is a maximum, which you can find out by differentiating this expression with respect to capital U. So, if I plot this power as a function of capital U, so it will show a maximum and then go down. So, it is 0 here and this is uj, somewhere it is a maximum. So, you can differentiate set equal to 0 and show that it is indeed a maximum. and then you will get capital U equal to, I think, uj divided by 3. Yeah. Okay, so, but then this result is for a single vane, and we also saw that immediately afterwards its position has changed. So, you can think of a limiting situation where you have a very large number of such vanes. So, that is how a turbine anyway is designed. You do not have a single bucket or a vane, because soon it is gone from that position. So, you will have another which will take its place. So, you will have in a typical hydraulic turbine, you will have many such vanes. Incidentally, this design was developed by a French engineer by name, do you know the name? Who knows the name of the French engineer who invented this configuration for converting jet speed into rotational movement of a shaft? How many French names do you know? You know from your knowledge of high school physics. I do not know if you have learned French names in this institute. Let us say from your knowledge of high school, if you attended a high school, that is. Maybe Carnot, do you know this name? Sometimes called Carnot, I am never sure. I think I was told it is Carnot, T silent, is a French name. In your mathematics, you keep encountering names like Laplace, okay, Poisson, Fourier, so a whole lot of French names. But here it is called a well, it's called a Pelton wheel. Okay. So, in a Pelton wheel you have a large number of buckets. So, if you have a single vane, then let us say force is equal to what was the expression? Rho A j capital U u j minus capital U square, where this rho A j u j minus u is the mass flow rate. So, you may write it as mass flow rate impinging on, this is mass flow rate as seen by the moving vane. But if you have many vanes, so that means the entire mass flow rate is now available to the device, and you do not have to write u j minus u. So, this is not force, this is power generated, right, power. So, that you write as rho A j u j capital U u j minus u. And in this case, for maximum power, capital U will turn out to be u j over 2. You had a question? You got the explanation later, Okay. Okay, so you can do that differentiation now or later, it's up to you. And this capital U, I think in the book they write it as omega r. Okay, so what is omega? Is the RPM. Oh, I shouldn't say RPM. RPM has units of rotations per minute. So you have to write what will be the units when you write velocity equal to omega r. What are the units of omega? Radians per second. Yeah. Okay. So radians per second times capital R. So the data will be given to you in RPM. You have to convert to radians per second. By the way, for the quiz tomorrow, please do bring your tables, but I have given all the required data in the question itself. You may not, 99.9%, you should not be required to refer to the tables. Okay. It's all there in the question. The data required is there in the question. Okay. So, this is a hydraulic turbine. By the way, there are other configurations of hydraulic turbines also, but this is the one that exploits this change in direction of the jet. And these are the expressions. Can you confirm that will this give u equal to uj over 2? It will give. How about the first one? I think it will give you, it's a cubic in capital U. So, you will have multiple roots, but only one of them will give you a maximum. You reject the root corresponding to u equal to capital U equal to uj. Okay. So, these little details I think I would request you to fill up. So, I will stop now, and today is a transition day, because on Friday we start energy equation, and there we talk about how gravitational energy can be converted to kinetic energy. But if any question, you can